All right, so latent heat. Latent heat is all about the energy needed to change the phase of a substance. We've dealt with specific heat, thermal energy, specific heat capacity, and that dealt with the amount of energy needed, right, to raise the temperature, specific heat capacity of 1 kilogram of substance, 1 degree Kelvin, or 1 Kelvin, excuse me. So it was all about raising temperature of a substance with specific heat capacity. With latent heat, it's all about changing the phase from a solid to a liquid, right? So this phase change right there from a liquid to a gas, okay? If we're going in a more traditional water idea, if we're not jumping from a solid directly up to a gas, if we were doing anything else, it would still be latent heat. And our equation is delta Q being change in thermal energy, right, or change in energy equals the mass that you are trying to change the phase of times your latent heat. Now, latent heat can represent multiple things. It's any type of heat that would be required, or any type of energy that's required to change the phase. And there are multiple different phase changes we have. So some of the most common phase changes that we see objects going through is melting and freezing, right? Going from a solid to a liquid, or vice versa, going from a liquid back to a solid. Whenever you're dealing with that, you're going to be dealing with something called heat of fusion, and that's what the latent heat is at that point in time, whatever the heat of fusion is. Like, if I remember correctly, ice to water is 334 kilojoules per kilogram, right? And so that's what would go there. And you would give this a sign positive or negative depending upon which way you were going. Whenever ice or liquid water is melting, it's actually taking in energy at that point in time. To melt it, you have to add heat, so it's taking in energy to melt, taking it from the environment or taking it from a Bunsen burner or whatever you have, so it would get a positive sign. Whereas if you were going vice versa, if you were taking it from a liquid back down to a solid, you would give it a negative sign, because it actually has to give off energy to go in that direction. Talk about that a little bit more here in a second. Heat of vaporization is whenever you change a substance from a liquid to a gas. So we're going that route on it, okay? And it works vice versa also, going back the other way. Same exact number for your latent heat. Heat of vaporization would go in for latent heat. Latent heat's kind of an umbrella term to cover any heat of something, phase change, whether it's vaporization, fusion, or any of the other phase changes that you could have. For example, going solid directly to a gas, and any other ones that are there would also go in latent heat. Now, let me explain something kind of odd and somewhat critical to understanding. While in a phase change, every last bit of energy that you give a substance goes into changing its phase or its state, not its temperature, aka whenever I am applying heat, let's say I have water, for example, on in a beaker on a hot plate, and I start heating it up, or let's say I'm starting with ice. And so the ice's temperature starts to increase, and then I get to 0 degrees Celsius. Now at 0 degrees Celsius, that is the quote-unquote melting freezing point of ice at atmospheric, of water at atmospheric pressure. And so at that point in time, all the heat that I add does not go any longer into increasing the temperature. Now it goes into breaking bonds formed in the solid, formed between the water molecules, to get it to become a liquid. So all the energy goes into breaking the bonds, and it won't actually start increasing in temperature, assuming that you're stirring it, right, so that you don't have pockets of warm and pockets of cold going on inside your mixture. It won't actually start increasing in temperature until all of the ice is melted, until every last bond is broken, and now we have just liquid water. Then the heat that you add will increase the temperature of the liquid until we get to 100 degrees Celsius if we're dealing with water, the boiling point, so to speak, of water, right, the vaporization point, to be a little bit more technical. And so then all the heat you add goes into vaporizing the water. If you have a boiling pot of water, that boiling pot stays at 100 degrees Celsius no matter what. It's still at 100 degrees Celsius until all the water is boiled off into steam. And then once you have that steam, then you can start increasing the temperature again, getting higher and higher and higher and higher. And if you get ridiculously high, which we couldn't do, we'd get to plasma, right? We're not doing anything like that in the lab. Now let me explain a little idea of what's going on with these bonds. When objects form a bond, it actually has a energy well. Lots of people tend to think of bonds having positive energy. Whenever two atoms come together and bond, they have positive energy, and it's not the case. They actually have, if you will, negative energy. They actually are fallen down, if you will, into an energy well. So imagine kind of gravity here, right? Two atoms kind of roll down into the hill together in an energy well, where this is the separation between the atoms, and this through y-axis is the energy. It requires you put in energy to get these atoms to start to separate, to get out of the well, so they get further and further and further apart. So that's the idea of why you have to put in energy, so a positive delta Q. Whenever you're going this way up through it, whenever you are melting or whenever you are changing, vaporization, changing from a liquid to a gas, and you're going to use a negative delta Q when going the other way. The thing is going to require that it gives off energy coming from a liquid down to a solid. It's got to give it off. Think of a freezer also. You put water inside of a freezer, liquid water inside of a freezer trying to freeze it. Well, that liquid water is actually putting out thermal energy into the freezer, giving it off into the freezer so that it can cool down. So it's heat is being transferred from hot, the water, to cold, the surroundings, and then the freezer's job is obviously to pump that heat away and then throw it outside of the freezer refrigerator, standard kind of heat pump style. All right, so now let me solve a couple of problems for you. All right, so now let's solve how much energy would it take to turn 2.5 kilograms of ice at -4 degrees Celsius all the way into steam at 120 degrees Celsius. So I want to apply enough energy, enough heat, that I take something from down here on our graph, specifically frozen water, all the way through this entire piece up to steam up there. Now, whenever you look at this, I have 5 pieces that I'm going to have to deal with. I have to deal with specific heat capacity of ice, 1 there. Then I have to deal with the phase change, 2 here, the phase change to get it from ice to water. Then I have to heat up that water, 3, right? Then after I get that water to its vaporization point up here, 4, I have to change it into a gas. And then once it's a gas, 5, I have to transition that, raise the temperature all the way up to 100 degrees Celsius. So what that means is I've got 5 different spots that I have to add up my change in thermal energy. Thermal energy total is going to equal the thermal energy needed to raise the temperature of the ice, plus the thermal energy needed to melt the ice into water. Now the thermal energy needed to raise the temperature of the water, plus the thermal energy needed to vaporize it, okay, plus the thermal energy, that's to convert it from liquid to gas, from liquid water to steam, and then plus the thermal energy needed to raise the steam all the way from 100 degrees Celsius up to 120 degrees Celsius. So I'm going to go ahead and substitute in my equations all of my raising the temperatures. This one, and this one is going to turn into mc delta T. And anytime I'm trying to change phase, the amount of energy needed to change phase, melting, vaporization, that's going to turn into ml. All right, so there you go. I went ahead and broke down delta Q to raise the temperature of ice as this. Notice, with mc delta T, specific heat, we're trying to raise the temperature and we're not changing state, thus mc, and there's a delta T on it. Whenever we're trying to change phase, latent heat, there is no delta T. We're not changing the temperature. So like with ice melting here, ml, specifically the latent heat of fusion, right? And over here, the latent heat of vaporization, trying to change it from a liquid to a gas. Also notice that the signs on these are positive here. The reason that they're positive is it's actually going to be taking in heat. We have to give it heat, so it's taking in heat. All of these are taking in heat. Now, with your standard MCAT, you don't necessarily have to deal with positive and negative because your delta T will do that for you. Here, though, you do, because there is no delta T to deal with. You're going to have to think about that. But since we're giving it heat, it's taking in heat, everything's positive. I looked up in the book table all of my latent heats, all of my specific heats for everything that I need. Remember, specific heats, latent heats, they are, pardon the slight pun, specific to each thing here on Earth, each molecule or each atom. By the way, it does vary a little bit with temperature, but not greatly. So you just look them up, right? And then you can use them in your equations up here. So now I'm ready to just start plugging in numbers. All right, so there's all the numbers substituted, and a couple of things I'd like to point out. You probably want to pause the video about now and kind of examine this entire thing, try to figure it out. Obviously, so many numbers, I had to go into 2 lines. I didn't have enough space horizontally here on this page to make it work. But a couple of things to point out. My latent heats of fusion and vaporization were in kilojoules. That's why such the large numbers here. Also notice how large heat of fusion is, 334,000 joules, right, compared to even an incredibly large specific heat of water, 4,187, right. Incredibly large heat of fusion, and look at the heat of vaporization, it's even larger. It makes sense that in car engines and other things where we need basic coolant, we end up using this right here. We end up using specific heat of water. We use water to keep it cool because it has such a large specific heat capacity. It's a great heat sink. But it makes even more logical sense to you if you think about it, why power plants, nuclear power plants, coal power plants, everybody else uses steam in cooling towers to actually transfer energy, right? They use cooling towers to then cool things off, because check out how much energy steam it takes to heat steam, liquid water into steam, and so thus how much energy it's going to give back whenever you're done there. So this is an incredible amount of energy there needed per kilogram latent heat of vaporization. So make sure to check this out, pause the video, try to check all those numbers out, comparing over here, making sure it makes sense. Notice final minus initial for your ice going final up to 0, minus -4 was the initial, so that becomes positive. And I'm going to go ahead and put down our answer. And you come out with the total amount of energy needed here to be, with sig figs, 7.7 times 10 to the 6 joules, 2 sig figs, right, is what I am given in this problem. 7.7 times 10 to the 6 joules, an insanely large amount of energy, especially if you put that in terms of standard motion kinetic energy. This is way larger than anything we would be dealing with standard cars or anything like that. Also, interestingly of note, about a little over 5.5 times 10 to the 6 joules. So a vast majority of this energy actually came right here from having to vaporize the steam, just simply because the vaporization of water, latent heat of vaporization of water, is so insanely large. All right, I want to really quickly work a equilibrium problem for you, thermal equilibrium problem that involves heat of fusion, heat of vaporization, so latent heat. But I do want to work this quickly for you. You will need problems like this to use as example problems to solve your homework. So I've got 5 ice cubes. I give you an average mass. Place into a glass of sweet tea. Sweet tea, 450 milliliters of sweet tea. We're going to consider sweet tea to be water because it pretty much is there. So we use specific heat of water. It was brewed at 58 degrees. We want to know what is the final temperature of everything. So let's go ahead and let's start working that. So equilibrium problem, meaning that all of my thermal energies, all my change in thermal energies added up has to come out to equal 0. So the latent heat of fusion, how much energy, right, the ice is going to take in to melt, right, is how much heat the water is going to give up. Now remember, delta T on this is going to be negative, going initial 58, final some other temperature there. So this is going to be giving it up. This is going to be taking it in. We're going to consider our 5 ice cubes to be at 0 degrees already and just melting. So we're going to neglect the increase, if you will, or that it could be at like -2, -4 degrees Celsius. We're also going to neglect that as this ice melts, it turns into water, and so that would add mass over here. So there would be technically a third delta Q in here for the water as it melts, as it warms up also, because 24 grams is a very small amount. Also of note, 450 milliliters, the conversion with density of water is 1. So every milliliter is 1 gram, meaning that we have 450 grams of water that will go in for our M right here. So remember, we had 5 ice cubes, converting the average mass of those ice cubes over to kilograms. Also, 1 milliliter equals 1 gram, thus we have 0.45 kilograms of water that's cooling down. We're looking for the final temperature here. Right now I'm going to need to distribute here. My final answer comes out to be 37 degrees Celsius, 2 sig figs, if I consider my 5 ice cubes to be exact, because you don't really have partial ice cubes necessarily there, so I have 5 whole ice cubes. So this is exact. That doesn't play into significant figures. We can talk about that in class if that's confusing to you. But here's 2 sig figs, 2 sig figs, 2 sig figs, so 2 sig figs here. In the end, this isn't enough ice, right? Because room temperature is somewhere around 20, 21 degrees Celsius, so your tea is still pretty hot. You're going to need more than 5 ice cubes to cool this tea down to hopefully below room temperature. That way you have, that's the whole idea of iced tea.